Up next in our kinematics or motion study is our kinematics equations, and here they are right here, all four of them. Actually, on the AP test on the equation sheet, there's only these three. This is an extra one that we've used in class occasionally. It's essentially the average velocity equation. This side says the displacement over time is equal to the velocity, or the average velocity, and this is the beginning and final velocities added divided by 2, which is the average velocity. So that doesn't show up very much on the exam, so just in case, it's there. All right, big thing about these equations is on the AP exam, there's going to be one, maybe two actual numerical problems with these on them. The rest of them will be semi-quantitative questions, meaning they're going to ask you when this thing changes, like you double the time, you double the velocity, what happens to the displacement, things like that. All right, so keep that in mind. Second thing is that these are only good for a constant acceleration. So if the acceleration is changing, these are no good. Next thing is, remember that in the up and down direction, we would put y's in here, right, for y displacement, y velocity, and so forth. And the acceleration would be g if it's in free fall, if it's a projectile, meaning that there's only one force acting on it, and that force is gravity downward. Okay, so remember that. So anytime you're trying to use these equations, build a data table, even if you only have symbols. All right, so let's look at a couple of examples, actually 3 examples. Here they are. You can take a screenshot of these and or pause the video and see if you can solve them first, and then I will solve all 3. So here's our first problem. You did solve it on your own, correct? Ooh, you better. You need the practice. Okay, so here we go. Here's our first problem. It says a small cart is rolling freely on an inclined ramp with a constant acceleration of negative 0.5 meters per second squared in the negative x direction. Okay, that's going to be important. At time equals 0, the cart has a velocity of 2 meters per second in the positive x direction. The cart never leaves the ramp. Which of the following statements correctly describes the motion of the cart? Okay, I find it's very helpful to draw a picture. I'm going to draw my cart like this. Since it's accelerating this way, this must be the positive x direction up this way. Here's my cart. And then it's moving upward at 2 meters per second with an acceleration this way of negative 0.5 meters per second squared. Okay? Now, whether we want to or not, whether we like it or not, we need to have a data table. So here we go. X naught, X, V naught, V, A, and T. I'm going to call where it starts X naught 0, since they didn't give that to us. We don't know how far it travels. We do know its initial velocity is 2 meters per second. We don't know the velocity. We do know the acceleration is 0.5 meters per second squared. And we do know we're talking about which of the following statements correctly describes the motion at a time of 5 seconds or greater than 5 seconds. So I'm going to start with 5 seconds and see what that gets me. 5 seconds or greater. Okay? Now look at our answers. It says the cart is traveling in the x direction and slowing down. Negative direction, slowing down, speeding up. So they're wanting to know about the velocity. So I don't really care about its position. I care about its velocity. So I want to know what its velocity is going to be like. So there's an equation that will help me out. V equals V naught plus AT with the initial velocity of 2 meters per second minus 0.5 meters per second squared times the time of t. All right, if I work that out, I get 0.5 negative meters per second squared. That's in the negative x direction. So the cart is now going back down the incline. So that means these two have to be wrong. Since it's going back down the incline, and the incline is tilted like this, that means it must be speeding up. So it can't be slowing down. So D is our answer. All right, problem number 2. Student throws a ball of mass m straight up with a velocity of v1 such that the ball reaches a height of y. All right, let me draw a picture of that. Here's the ball being thrown straight up, velocity of v1. It goes up, turns around, and comes back down. This height is y. Student 2 has a ball that has a mass of half m. What velocity must the student 2 throw the ball so that the ball travels twice as high? All right, in this particular problem, this problem doesn't really have any numbers. So this is what's called a semi-quantitative problem. Semi-quantitative. Quantitative meaning numbers, but semi meaning we're just looking at the equation relationship and there's not actually any numbers put in the equations. We're looking at the relationship from the equation. So we still have to build a data table. So here we go. X naught, well, how about y naught, y, v, y naught, v, y, a, and t, since we're going up and down. I'm going to call up positive, since the ball's going up and down. We're going to call that y naught equals 0, so it starts at 0. It gets to a height up here of y. Its initial velocity is v1. The velocity at the top is 0 because it stopped at the top. The acceleration will be negative g. And I don't know anything at all about the time. Okay, since I don't know anything about the time, I can't use an equation that has time in it. So let's take a look at this one. V squared equals v naught squared plus 2ax minus x naught. Now, let's get rid of everything that's a 0, or plug it in as 0. So that's 0. And let's see, that's our final velocity, 0. Sorry, I put x's here again out of habit. These are really y's. So it's 0 equals vy initial squared plus 2ay. Let's plug in what we know. We know that 0 equals the initial velocity squared plus 2 times negative g, and then it goes to a height of capital Y. I'm going to rearrange this, move this to the other side. The negative goes away. I get v1 squared equals 2gy. And then I'm going to square root it. v1 equals the square root of 2gy. All right, at this point, we want to know what happens, what we need to do to get this ball to go twice as high. Notice, we have mass in here. I don't see mass anywhere here. Hey, this mass is a decoy. They just did that to see if we were paying attention. This object is in free fall. It's a projectile. Okay? That means the acceleration will equal g downward. Now, free fall, projectile, this only occurs if the object has only one force, the force of gravity acting on it. So no air resistance, nothing else. So it has to be in just gravity pulling it down. Then this will be true. And the mass never matters. Everything accelerates down at the same rate. So the mass is irrelevant. So we can see that v1 is proportional to the square root of y. So if we want it to go twice as high, that 2 is square rooted, so we need a square root of 2 factor. So our answer is that the second velocity has to be the square root of 2 times the original velocity to get it to go twice as high. Now, in the video many of you watched just yesterday from College Board, you saw Greg Jacobs do something called factor of change. So let's solve it that way, just so you can see that this, some of you may like this method better. It's the same thing. Factor of change. So the way it works is you have to do all this same background work to get to here, to this equation. So all of this is the same. You get to here, and you develop an equation that shows the relationship between the variable and what you want to find. Okay? So I want to find out what this v is, the new velocity is. But this is the equation that tells me how it's related to everything else I know. Now, in the factor of change method, is everything that's constant, you have a factor of 1 because it's not changing. So like 1 times g is g. All right, it's not changing. Everything that's changing, you multiply by the factor that you want. Okay? So here's how it works. It sounds complicated. It's actually really simple. So to the number 2 is not changing. So that's a factor of 1. G is not changing. So that's a factor of 1. Y, we want to double. So we have to multiply it by a factor of 2. And then the whole thing is square rooted because that's the relationship. And we end up with the square root of 2. So that just means if we want to get twice the height, we have to multiply v1 by a factor of square root of 2. All right? So if you like this method better, you go right ahead, or you can set up a proportionality and see how it works, just like we did in class. So here's our third and final example. A rock is dropped from rest from the top of a high cliff. After 1 second, the rock has fallen distance d, is traveling velocity v. How far has the rock fallen when its velocity is 2 seconds? Okay, so this is another semi-quantitative problem where we're trying to find out something using equations, but without actually substituting numbers into the equations. So let's build our data table again. Actually, let me draw a picture first. Here's my cliff. It's a very high cliff. Here's my rock. It starts right here. I'm going to call this y equals 0, and I'm going to call down positive because that's going to make my math simpler. And it's going to fall downward. And it's a very high cliff, so I don't have to worry about it hitting the ground. And they don't mention anything about air resistance, so I'm going to neglect it. Assume it's small. So set up my data table. Y naught, y, v, y naught, v, y, a, and t. So I'm going to start at 0 position. It's going to fall a distance d. I'm going to start with a 0 velocity because it starts at rest. And then it's going to end with a velocity v. It's going to be accelerating downward with an acceleration of g. Now, is that g positive or negative? Well, since we called down positive, that'll be positive. And we know the time begins at 1 second, but we're going to change it. We want to change it to 2 seconds and see what will be our new velocity and our new displacement. So let's find equations that relate time to our distance and time to our velocity. So let's do the distance one first. So let's see. How about this one? Y equals y naught plus vy naught t plus 1/2 at squared is our equation. Since it's in the y direction, I put y's in. Let's plug in everything we know. We know it starts with a 0 here and a 0 here. So that's y equals 1/2 at squared. And now let's plug in our variables. We know it's going to fall a distance d, 1/2 g t squared. So if we do the idea of proportionalities, we can see that d is proportional to t squared. So if I go from 1 second to 2 seconds, I'm doubling the time, but time is squared, so I'll get 4 times the distance. If you want to use the factor of change method, our same equation is d equals 1/2 gt squared. 1/2 is not changing, factor of 1. G is not changing, a factor of 1. T is being doubled twice the time, and it's squared. So our factor is 4. So our distance will be 4 times. The factor of change for distance is 4 times bigger if we double the time. All right? So now let's look at velocity. Oops. Here's our equation for velocity. So v equals v naught plus at. Our initial velocity is 0. So this one's easy. V equals a times t. V is proportional to t. So if we double the time, we will double the velocity. Or if you do the factor change method, v equals at, same thing. And the factor for a is it's not changing. And our time is being doubled. So we get 2. So the velocity will be doubled. And there we go. There are our 3 equations. Our 3 problems. And I hope you are doing well in your review. All right, everybody. I hope you enjoyed those 3 review questions. I hope that answered some of your questions and jogged your memory on other things. So hang in there. You're doing great. Up next is kinematics graph.